So today's 8.4. We're going to learn about the Cartesian equation of a plane. And what I'm going to do in deriving it is very similar to how I derived the Cartesian equation of a line. So here we have a plane, and on the plane we have a known point and an unknown point. And then I've drawn a normal to the plane, which has a direction vector A, B, C. Now if we connect the points, P, naught, and P, right, and subtract the coordinates to get our position vector, we know that that line and the normal for the plane are perpendicular. And if they're perpendicular, we can take their dot product and set it equal to 0. And that's exactly what we did before to find the Cartesian equation of a line. But in this case, what we do is when we take the dot product and expand it, here's all of our constants. So we can set all of that equal to one constant, d. And we get the equation ax plus by, but now we have plus cz plus d. This is why we couldn't just add a z term to our equation of a line and say, hey, that's the equation of a line in 3 dimensions. Well, no, because it describes a plane, not a line. And also notice, the great thing, is that a normal to the plane simply has our coefficients for x, y, and z right there, a, b, c. So we'll be able to quickly pull out normals for a plane. And that's useful because if we have two parallel planes, then their normal vectors will also be parallel. And if we have two perpendicular planes, well, their normal vectors will also be perpendicular. But first, before we get into problems like that, let's go over some examples of how to take, for example, our Cartesian equation of a plane and convert it into a vector and parametric form and vice versa. So first, let's start with this one. We need a bit more room, so I'm going to go to the side here. And here we have a Cartesian equation of a plane. Now there's two methods that we can do to figure out a vector equation and corresponding parametric equations. First method, so I'm going to write method 1. And again, this lesson will be very similar to how we did it for a line. Okay, so method 1, we are just going to choose, let's say y is going to be some scalar s. So we're basically choosing parametric equations for y and z. Z will be t. And then we're going to substitute those back into this equation, and I'll do that here. X minus 2s plus 5t minus 6 equals 0. So rearranging, we can solve for x, and x is just 6 plus 2s minus 5t. So there you go. There's our parametric equations for y, z, and x, and we can write that as a vector equation. So r equals, so our first point is we have 6, and then no constants here, so 6, 0, 0, plus we have our first scalar quantity, s, and then over here, oh, I forgot the s here, minus 2s. So we have 2, 1 for y, and 0 for z. So 2, 1, 0. I'm running out of room, so I'm just going to go down here, plus t. And for t, we have minus 5. And then 0 for y, and 1 for z. So there you go, our parametric and vector equations. All right, that's method 1. Let me show you method 2. Method 2. So method 2 is all about choosing 3 points on the plane. So for example, our first point, we just need to say choose something for y, choose something for z. Let's choose easy points, so 0 and 0, and then, okay, what would be the corresponding value for x on the plane? So to do that, we substitute y is 0 and x is 0 back into this equation. So we get x minus 0 plus 0, then minus 6 equals 0. And therefore x equals 6. So there's our first point. Let's call that point A. And it is 6, 0, 0. Okay, I'm going to scroll down a bit here. I don't have much room left. Point B, let's choose, for example, y is, again, you can choose anything, but choose something easy. Z, we can pick 0 again. And then x, substituting our new y and z, we can figure out what the x coordinate would be on our plane. So we have x equals, well, bring this over, so 6 plus 2y, and y is negative 1, so plus 2 times negative 1, and z is 0. So that gives us x as 4. So our next coordinate, which we will call b, is 4, negative 1, and 0. Okay, I'm just going to use this space over here to find our last coordinates. Let's have y as, we'll do negative 1 again, and we'll make z 1. You can do that yourself, and you'll see that you'll get x to be negative 1. So that's our third point, C, which is negative 1, negative 1, and 0. Now we have 3 points. Now in our previous lesson, we learned that you can describe a plane with 3 points. How do you do that? Well, we pick 2 position vectors, so we can figure out what AC is. Then we can also figure out what AB is by taking the difference in their coordinates. So AB would be, well, 4 minus 6 is negative 2. A negative 1 minus 0, so that's negative 1, and then 0. And AC would be negative 7, negative 1, and 1. And there you go. Now you have 2 direction vectors, AC and AB, and we have a point. Actually, we have 3 points. Use whichever one you like. I'll use point A. So I'll say our vector equation then is, if I use A, that's 6, 0, 0. You don't have to. Remember, there's an infinite number of equations you can get to describe the plane. Plus S, actually should use something different from what I used. So just to recap, once we have our position vectors, we can add those in with some scalar multiple and choose any point that we want, either A, B, or C. We could have also chosen different position vectors. Remember, we can have an infinite number of ways. Okay, so thanks for pointing this out. Our point C, which we solved for here, should have had a z coordinate there of 1. We wrote it down there, but I didn't write it down there. My bad. So we'll just fix that and put our 1 there. All right, so moving on. Now how can we go from this vector equation and create a Cartesian equation? So let me rewrite this vector equation over here so I have some room. So it was R equals, so we have a point, a known point, and then we have 2 direction vectors, S, and let's go with T, just because it looks like my plus, and that'll just confuse everybody. All right, so those are our direction vectors. Let me just call them A and B. So A is 1, 0, 2. That's one direction vector. And our other direction vector B is negative 1, 3, and 4. So what you could do is you can first find their cross product. Why? Because I want to know a vector that's perpendicular to this plane. Why would I want to know a vector perpendicular to the plane? Remember, the coefficients in standard form A, B, C is a vector perpendicular to the plane. So we can do the cross product, which we've learned before. And if you want, you can draw your diagram to help. But we'll have 0 minus 6, negative 2, subtract 4, and 3 subtract 0. So that gives us negative 6, negative 6, and 3. And what we can do there, kind of like how we put a fraction into simplest form, we can pull out a scalar multiple and write this as 2, 2, 1. Therefore, our normal vector to this plane is 2, 2, 1. And again, you don't have to pull out the negative 3. It's like a fraction. 2 over 4 is the same as 1 over 2. The answer is going to be right either way. It just looks nicer. So our standard form equation, which is ax plus by plus cz plus d equals 0, has the coefficients a, b, and c. So we know what a, b, and c are. So let's write those in. So we have 2x plus 2y plus 1z, or just z, plus d equals 0. Now to figure out what d is, we need a point on the plane. Well, they give us a point on the plane right there in our vector form of the equation. So let's substitute those numbers in and solve for d. So when we do that, we'll have 2 times 1 plus 2 times 2 minus negative 1 . Oh, you're right. I missed another minus in there. That should be negative. That should be negative. And therefore, that should be negative. All right, so minus negative 1 plus d equals 0. Right, and then solving for d, we get d equals negative 7. Therefore, our equation is 2x. I'm going to write it over here. So therefore, 2x plus 2y minus z minus 7 equals 0 is the Cartesian equation for the plane. All right, our first sample question, again, there's two ways to do this. So here we have a point on the plane and a normal vector to the plane. It's very similar, the same two methods I taught you when we did lines. We need to find a Cartesian equation to this plane. So we could use the method that we just did. Since we already have the normal, we don't need to do a cross product. And we can just say that this is our x coefficient, this is our y coefficient, and that's our z coefficient. So that gives us minus x plus 2y plus 6z plus d equals 0. And then we can use that point they give us to determine what d is. So we'll have minus 1 plus 2 times 2 plus 6 times 2 plus d equals 0. And solving for d, we get d equals 2. Negative 15. Therefore, our equation is minus x plus 2y plus 6z plus d equals, oh, sorry, we know what d is now, minus 15 equals 0. Now, there is another way to do this. The other way of doing it is to realize, okay, we have a known point A. Let's take an unknown point P, which I will give the coordinates x, y, and z. And then I can find the position vector AP, which would be x minus 1, y minus 2, and z minus 2. And then, since this position vector is on the plane, it'll be perpendicular to the normal. So I can do the dot product with AP and the normal vector and set it equal to 0. That'll give us negative 1 times x minus 1 plus 2 times y minus 2 plus 6 times z minus 2 equals 0. And then you can distribute into each bracket and expand, and recommend you try it. You'll get the exact same equation we got above. Minus x plus 2y plus 6z minus 15 equals 0. So 2 methods to do that one. Part 2 gives us 3 points on the plane. Okay, so if we have 3 points on the plane, what we're going to want to do is to figure out 2 lines on the plane, right? 2 direction vectors. Let me change my colors. Here we go. So why don't we do AB? So we'll figure out what AB is. And that would be 4. Right? So 3 subtract negative 1, so 4. And 0 and negative 1. And we can do AC. You can choose any combination, really, as long as they're not parallel. And we'll get negative 1, negative 5, and 1. Now that we have those 2 vectors, I'm going to move over a bit here. We need to find a normal to the plane. Well, to find a normal to the plane would be any vector perpendicular to both of those vectors. So there's our cross product. So we're going to do AB cross AC. Okay, and you can draw your helpful diagram there. And we'll get 0 minus 5, 1 minus 4, and negative 20 minus 0. Which gives us negative 5, negative 3, and negative 20. But if you don't like negatives, pull out a negative 1 as a scalar multiple there. So 5, 3, and 20. And therefore, our normal vector to the plane, n, is 5, 3, and 20. And then this goes back to the method we have before. If you have a normal vector, then you know the coefficients of our standard form for a plane. And since we have 3 different points, pick one, and we can solve for d. I'll just go down here and do this. So our normal gives us 5x plus 3y plus 20z plus d equals 0. And since we know a point, let's use point A, I guess. We can use 5 times negative 1 plus 3 times 2 plus 20 times 5 plus d equals 0. Solving for d, we get d equals negative 101. So our equation then of the plane in Cartesian form is 5x plus 3y plus 20z minus 101 equals 0. All right? After all that, we should be pretty good at going back and forth between Cartesian and vector form. So, example 2. The first one says we have 2 planes, so pi 1 and pi 2. Show that they're perpendicular. Now this is where we're going to use the normals to help us. So if the planes are perpendicular, their respective normals are also perpendicular. So I'm going to write this over here. Our first normal will be, again, look at the coefficients, 2, negative 3, and 1. So 2, negative 3, and 1. And our second normal, looking at the coefficients, is 4, -3, and -17. 4, -3, and -17. Those are our two normals. Now, if they are perpendicular, we can show that by proving that the dot product between the two normals is 0. So let's figure that out. So 2 times 4 is 8. -3 times -3 is +9. And 1 times -17 is -17. Does that equal 0? Yes, it most certainly does. So those two vectors, pi1 is definitely perpendicular. Sorry, those two planes are definitely perpendicular to each other. Now question 2 is asking, are they parallel but not coincident? Remember what that means. Parallel, but do not lie on top of each other. So I want to know that they're different planes. And this we can actually just look at. This one's a nice question, because notice that their coefficients are all the same. So their normals are both 2, -3, and 2. If they weren't the same, all you really need to do is still show that one normal, 3, is some scalar multiple of the other normal. If they are, then yes, they're parallel. In this case, they certainly are. It's just k has a value of 1. Now, take it one step forward and look at their constants. Their constants are different. If their constants are different, then they are not coincidence. If they were the same, then they would be the exact same equation and the exact same plane. So they would be coincident. So in this case, yes, they are parallel, but they are not coincident. So for our last example, we can take this one step further, and we can find the angle between two planes that intersect. Now, if the planes intersect, their normals have the same angle between them that the planes do. So, look at their normals and use the dot product to figure out the angle between them. Let's first figure out the normals. Let's call it N1. Oh, that's the laser. So the normal for our first plane is our coefficients 1, -1, and -2. And for our second plane, the coefficients are 2, 1, and -1. So there are our two normals. So if you remember the geometric dot product, I'll write it again down here. We can rearrange so that cos theta equals the dot product between N1 and N2 divided by the magnitudes of those vectors. Okay, so taking their dot product, we have 1 times 2, which is 2, plus -1 times 1, which is subtract 1, plus -2 times -1, so add another 2. Now remember how to find magnitudes. We're going to take the square root of, for N1, 1 squared plus 1 squared plus -2 squared. Right? So that's 1 plus 1 plus 4, which gives us the square root of 6. And same for this one, 2 squared is 4, 1 squared is 1, -1 squared is 1, so again, 6. So this gives us cos theta is equal to, that's just 3 over 6, which is just 1/2. And if you remember your special angles, that means that theta is 60 degrees. But it would also be okay to say it is 120 degrees. Usually when you state the angle between planes, you state the acute angle, but it's also fine to state the obtuse angle as well.